This is my presentation on the physics of falling objects. So the problem we are given is to track the fall of an object from rest and then compare this data to two other physics models we will develop using the gravity or the force of gravity and drag. We are interested in doing this because it will show us which model will more accurately predict position, and then it also gives us a better understanding of the forces of gravity and drag that play a major role in engineering applications. I don't have very much experience in physics labs or Python, but I've spent 2 semesters in chem labs, which help me better analyze the data. To roughly break down my methodology, I'll be dropping a plastic food container from rest above the ground, and then I'll track it using tracker software. And I'll develop 2 physics models using Newton's second law in the Python coding language, and I'll compare the observed results and then the 2 models I've developed, and then I'll compare the results and I will discuss that and a few related questions. So the background information for the data collected is I calibrated my distance by measuring the diameter of the container, and then the y-axis goes through the center of the container, and then the x-axis is the floor. The upward and rightward directions are positive. So for Model 1, which only includes gravity and is based on Newton's second law, we know that acceleration equals force divided by mass, and for us, Fnet will only equal mass of our object times gravity, and we'll use the kinematic formula that uses force, which is velocity equals v naught plus Fnet divided by mass times delta t to update our velocity, and then we'll update our position with y equals y naught plus velocity times delta t, and this will be repeated for every delta t until y. All of my initial conditions are listed, where I have the initial mass as 2.5 grams, the initial position is the y value is 1.216, and then the initial velocity is 0 in every direction. And this model does not involve drag, so the proportionality constant b will equal 0. And the position and velocity update formulas based on Newton's second law are shown below. They're essentially the kinematic equations I have already listed, equal 0. And so I made this to illustrate that drag is in the opposite direction of velocity and gravity, which is why in Model 2 the force will not be constant, because the force of drag is in the opposite direction of gravity, so it'll be like slowly eating away at it. The Model 2 is based on Newton's second law still, but it involves drag and gravity, so Fnet is now the force of gravity plus the force of drag. And we've been told the drag force is proportional to the square of velocity in the opposite direction, so the force of drag equals b, our proportionality constant, times velocity squared, and then times the negative unit vector of velocity because it's in the opposite direction. And then we'll use the same kinematic formulas as for Model 1. The initial conditions are the same. Since drag is present and pointing in the opposite direction, the unit vector of b is 0, -1, 0. And we were instructed to vary our value of b until it provided the best fit for our experimental data. And for my data set, that meant that b equals about 0.1. And then based on the previous formulas, I found the net force where Fnet equals Ft plus Fg. And then the kinematic equations are the same as before. And you can see on my chart that the model with gravity and drag fell too slowly, while the model with only gravity fell too quickly, and my observed position was about equally in between them. So neither model correctly predicted the position of the food container. The inaccuracy probably has a few causes. The object was not a perfect sphere, so forces were not evenly distributed, and the object became blurry during the descent, so it's possible I inaccurately placed the center of mass of the object while tracking. In the future, my observations could be more accurate by using a spherical object of a darker color over a lighter background, so I can ensure I was tracking it correctly and that the forces were even. To move on to the first discussion question, terminal velocity occurs when an object is moving downward so quickly that the force of drag becomes equal to the force of gravity, which makes the net force 0 and the acceleration 0. So once that velocity is reached, it'll be maintained. And neither model appeared to reach terminal velocity before reaching the ground. Model 1 has constant acceleration, so it would have never reached terminal velocity, but Model 2 does not have constant acceleration. The acceleration is decreasing because of drag. And if given enough time, it would have reached 0. You can see that Model 1 is a straight line down, but Model 2 is curved and decreasing. And so to move on to the other discussion question, we are asked to imagine if the object was thrown down instead of dropped, which would mean the object would have an initial velocity that is not 0. Terminal velocity is only dependent on drag force and gravity force, so changing the initial velocity will not change the terminal velocity. But since the object would have an initial velocity, the terminal velocity would be reached faster. And so you can see that the two graphs I made support my statement. The first one, where I didn't change anything, you'll see the initial velocity is 0 and it approaches -5 meters per second and never goes beyond it. Once it reaches that, it stays there. In the second model, I added an initial velocity of -1 meters per second in the y direction, so you'll see it starts lower in the graph, and so it gets to -5 meters per second faster, but once it gets there, it once again stops. Thank you for listening.